Hello everyone, and welcome to this video on sections 6.3/6.4, but it's only going to be on the objective called Taylor and Maclaurin series. So in this video, I'm going to be taking you through part of a Newton-Alta assignment on Taylor and Maclaurin series. So I looked through, it's one of these assignments with 5 objectives, and these are pretty heavy topics. So I've decided to split up the videos, make multiple ones for this assignment, based on the experience I've had making really, really long videos for previous Newton-Alta assignments with 5+ objectives. So this video will specifically be on the objective Taylor and Maclaurin series. So please understand that the questions I see in this video may not be the exact same questions you see, for this objective when you work on the assignment yourself, but hopefully the problems are similar enough so that watching me do them here will help you when you work on them on your own. Okay, so here's our Newton-Alta assignment, and you'll see the title of the assignment without the word preview in the upper left-hand corner. In the upper right-hand corner, you'll see the mastery bar that tells you how far along you've gotten. Again, I'm not going to complete the whole assignment in this video. If you look at the activity log, right, that little thing next to it, there are 3 major, 4. So this will be in 4 videos. I'm going to do this in 4 parts. The first video you're seeing here is on these Taylor and Maclaurin series, this bold objective. So I've got find a Taylor or Maclaurin polynomial for a function, and then estimate a function using a Taylor or Maclaurin polynomial. I'll explain what all those are. And I will bring up over the next day or two videos related to the other 3 bold headings in this assignment. All right, that's just so that the video is not insanely long. All right, then underneath that on the main page, you have the current objective, and then a question related to the current objective. And at the bottom of every question, you'll see a feedback button. If you see any typographical errors or problems with the answer explanations or whatever, you can send feedback directly to Newton, and hopefully someone will help you out and help you fix your issue. Next to that, you see the instructor cheat button here. You will not have this, right? This will not be there. It's for instructors only. But next to that is a more instruction button. All right, you can use this if you're struggling with a topic or a particular objective. Click on more instruction. You'll be taken to a page with reading to do or videos to watch or both. And then you'll be given questions related to that instruction, and you can work on those questions while the instruction is still up for you to review. And you can get through the assignment this way. You can work with the more instruction available every single time it comes up. All right. So the first of these 2, again, I'm doing just these 2 sub-objectives here for this big heading Taylor and Maclaurin series. The first 2 of the sub-objectives, find a Taylor or Maclaurin polynomial for a function. All right, so I'm going to describe, what is a Taylor polynomial, what is a Maclaurin polynomial, and also a Taylor and Maclaurin series, power series to represent a function. So we'll start with that. So first, the Taylor series representation of a function, right? Some power series that should converge for certain values of the input to a given function. Right, so Taylor series representation of a function, say, f of x. All right, so I'm just going to write it up. I'm not going to go into the development of it. If you look in your textbooks or the more instruction, the textbook I'm particularly thinking of that's tied to the more instruction in Newton Alta is the Calculus Volume 2 or Calculus 2 textbook from openstacks.org. That's STAX, openstacks.org. So if you go to section 6.3 there, you'll see the development of this. But I'm just going to write up what a Taylor series representation is. So f of x should be able to be expressed as some power series in the following way. So the sum from n equals 0 to infinity. And then you have your coefficients. Now the coefficients will look like this. The value of the nth derivative of f, right? So this is the nth derivative with the little n in parentheses here. At x equals a, right? So this is going to be a power series centered at x equals, some value called a. So I have the value of the nth derivative at a divided by n factorial. These are the coefficients. And then this is multiplied by powers of x minus a, right? So times x minus a to the nth power. And not only will we be able to represent the function as a power series centered at some value a like this, but we'll then also have to find the interval of convergence and radius of convergence, right? The power series doesn't always converge, right, to some function value. It might diverge. So I'll say out to the side here with radius of convergence r, which we'll have to find sometimes, right? Now r could be 0, and then the series only converges at the center, right, at x equals a. R could be some non-zero finite value, so then the interval from a minus r to a plus r will contain values of x that'll make the series converge. And then r could be infinite, right? So the series could converge for all values of x, all real x. Now, of course, the discussion of this interval and radius of convergence was back in section 6.1, 6.2, if you want to look at those. Okay, so yeah, you might have to determine this interval and radius of convergence on your own. But anyway, if I write out the first several terms of this, this would be, the value of the 0th derivative at a. Now, the 0th derivative is just the function itself. So the value of f at a, divided by 0 factorial. Now, remember, 0 factorial is defined to be 1, times x minus a to the 0, which should be 1 as well. So the first term, the constant term, is just the value of f at the center, the value of f at a. Plus, then when n equals 1, we'd have f, the first derivative, so f prime at a divided by 1 factorial. Now, that's just divided by 1, so I'm not going to write that. Multiplied by, our x minus a to the first power. So there's the first power term of the power series. Plus, and then when n equals 2, we'd have the value of the second derivative, f double prime, or you could have a little 2 up here with parentheses around it, at a divided by 2 factorial, right, which is just 2, but I'll put 2 factorial here, times, x minus a squared, and so on, right? You would keep doing this. This is called, again, a Taylor series representation of a function f. Now, a Taylor polynomial, right, in the title of this objective here, we see, find a Taylor or Maclaurin polynomial for a function. They'll talk about I'm going to use capital N because I'm already using lower n here. If they want the nth Taylor polynomial, another way I could say this is the nth degree Taylor polynomial. All right, this is going to be abbreviated P sub cap. Now again, I'm using capital N. I think they use little n in the book. Of x, right? It's going to be some polynomial function, and all it is instead of doing the infinite series, the whole thing, we just go up to capital N. We go out until we get x minus a to the capital N power, and we'll have some sort of nth degree, capital nth degree polynomial. This is simply the sum from little n equals 0 to capital N of, and then the same junk, right? It's the value of the nth derivative at x equals a divided by n factorial, and then times your powers of x minus a to the, again, little n here. And, this is not infinite. This is finite. This is going to capital N. So this is an approximation of the function. All right, what we're going to use these Taylor polynomials for is to approximate the function f, the value of the function f at certain values of x. So these are all Taylor stuff. Taylor series, infinite series, Taylor polynomial up to just the nth power, capital Nth power. Now, as soon as I call the center 0, if you let a be 0, center the series at 0, then the Taylor series is called a Maclaurin series, right? So a Maclaurin series is simply Taylor series centered at 0. So I'm replacing these a's with 0. So let me write that up for you, and then we'll get to our problem. So a Maclaurin series is simply a Taylor series centered at x equals 0. So the Maclaurin series for a function, right, f of x is going to be the sum from little n equals 0 to infinity, and then the value of the n, the coefficients look like this. It's the value of the nth derivative, right, whatever little n is, at 0, right? This time a is 0, divided by n factorial, and then times, powers of just x minus 0. So just x, times x to the nth. And of course, we, after writing a Maclaurin series for some function, would more than likely have to state where does that series converge, right? We would have to find some sort of interval and radius of convergence. So I'll just say with radius of convergence r, that we'll have to determine ourselves, right? But depending on the function we're looking at. All right, if you wrote out the first several terms here, again, the first term would just be f of 0, the value of f at 0, plus the value of f prime at 0 times x to the first, plus the value of the second derivative at 0 divided by 2 factorial, right? This should be divided by 1 factorial divided by 0 factorial, but, that's just 1 and 1. And then divided by 2 factorial times x squared, plus, the value of the third derivative at 0 divided by 3 factorial, or 6, times x cubed, and so on, right? Some infinitely long polynomial. And then, of course, like a Taylor polynomial, a the nth, I'm using capital N again, the nth Maclaurin polynomial or nth degree Maclaurin polynomial is just doing the Maclaurin series out to the whatever capital N power is. Right. So again, this will be denoted like the other one as P sub n, right? Some polynomial with an nth degree. And if it's Maclaurin, it's just the Taylor one centered at 0. So we're going from n equals 0 to capital N of, and then the coefficients once again are the value of the nth derivative at 0 divided by little n factorial times x to the little n. And yeah, if you were to write out all these terms, it would stop at this capital N. You'd have an nth degree, right? Capital nth degree polynomial. And this should be an approximation, right? This isn't the entire series, but this should be an approximation of our function, right? And then we'll see later, in another objective later, we talk about the error in this approximation. How far off of the actual function value could it be? But we'll talk about all that later. Right, but these polynomials, these Maclaurin polynomials, these Taylor polynomials, right? These are used to estimate the value of a function at certain inputs, at certain values of x. All right, so I'm going to keep writing those up or bringing those pages back. So now our problem, right, with this first question, find the Maclaurin polynomial p sub 1 of x. So that's just the first degree Maclaurin polynomial. So I'm going to have a linear function here, a linear polynomial. And the function we're writing a series or a Maclaurin polynomial for is, f of x equals 1 over 4x plus 8. So we got this. F of x equals, 1 over 4x plus 8. And since I'm going to be doing derivatives, I'm going to think of this as 4x plus 8 to the negative 1 power. Right? That's our function f. Now the p1, right, they're saying p1 of x, they want the first, Maclaurin polynomial is what they're asking for. p1 of x. So again, all that is the following. It's this sum from little n equals 0 to 1. All right, we're just going out to the first power. And then what I need after that is, again, every term looks like this. You got the value of the nth derivative, right, whatever little n is. And if it's Maclaurin, that means it's centered at 0. So I'm taking the value of these derivatives at 0, dividing by n factorial, and then times x minus a. Well, a is 0, so x minus 0, x minus 0 is x to the nth power. So this should be, again, just f at 0 for the first term, plus, and then when n equals 1, f prime at 0, the first derivative at 0 divided by 1 factorial times x to the first. And that's it. That's all they want. We just need to find f of 0 and f prime of 0. So if that's f, right, f of 0 is simply 1/8, right? 1 over 0 plus 8. So that's going to go here, right? That'll be the constant term of my linear Maclaurin polynomial. And then I take the derivative, right, and then plug in 0, and we'll get the coefficient of x to the first. So f prime, right, would be, negative 4x plus 8 to the negative second power, but then chain rule, I got to also multiply by the derivative of 4x plus 8 with respect to x, that's times 4. And if I want to rewrite this, this would be negative 4, right? Negative 1 times 4. over, 4x plus 8 squared. And then for this coefficient of x in my Maclaurin polynomial, I'm just plugging in 0. What's the value of f prime at 0? Well, that'd be negative 4 over, 8 squared, which is, of course, negative 4 divided by 64, which would be negative 1/16. Right, 4 goes into 64 16 times. And that's going to go, here. So this Maclaurin polynomial they're asking for, right? P1 of x is, f of 0, which we saw was 1/8, plus f prime of 0, so minus 1/16 times x. And this should be approximately the same as the function f near the center. I'll say, near x equals 0, right? Because this is the Maclaurin series. It should be around 0. And you can see that now. This is basically the tangent line. All right, remember f of a value plus f prime of a value times x. That's going to be the tangent at x equals 0 to this graph. Watch. So that's what it means to be near, right? The graph of our line, the graph of this linear function will be, close to a nice approximation of the graph of f at x equals 0, right? Or around x equals 0. And I'll show you that in Desmos. Let me actually make some room here. And so here was our function, right? F of x equals 1 over 4x plus 8. And then let's just look at it near 0 here, right? So here's the point. Here's 0, 1/8, right? That's 0.125, 1/8. Now let me put in my polynomial. P of x, right, was equal to 1/8 minus 1/16 x. And look at that. You see how that near 0 here, the blue line is very closely approximating the red graph, right? It's pretty much on top of it for this portion of it. Now, of course, as you go further away from 0, the blue line gets starts to deviate from the red graph, so the approximation is not as good. But near 0, near this point 0.018, the blue line looks pretty reasonable as an estimate to the red graph, to our function. So back in the assignment, this P1 of x, right, this first degree or first Maclaurin polynomial is, 1/8 minus 1/16 times x. All right, then after you submit a question, right, submit an answer, you'll be given some sort of answer explanation. Please go over these. Just, if you got it right, make sure you got things correct for the right reasons. Or maybe they do something in the answer explanations that you really like, and you want to try for future problems like this. And of course, if you got it wrong, definitely read through the answer explanations. Try to figure out, hopefully you can figure out where you went wrong, why you were wrong, and you can fix it for future questions. Great. All right, so now I'm in the other sub-objective from this big one, right? Again, we're just going to be going between these two here in this video. So estimate a function value using a Taylor or Maclaurin polynomial. So once again, I'm asked to write up a Maclaurin polynomial here. It says use the fourth Maclaurin polynomial or fourth degree, right? And we'll have a fourth degree polynomial function for the function cosine of x. And use the fourth Maclaurin polynomial to estimate the cosine of pi over 15 radians, right? And round your answers to 4 decimal places if necessary, right? So probably a calculator going to come involved here. Yeah, so let's take a look, right? Here's the function we're given. We have f of x equals cosine x. And they're asking us to use, I'm going to find the fourth Maclaurin polynomial. Again, I'll write the word Maclaurin next to it. That means it's centered at, 0. Center is 0. And then we'll use this to estimate the cosine of pi over 15. Now, you can already do pi over 15. Well, not really. No, pi over 15 isn't that nice. That's 12 degrees. I was thinking more of 15 degrees you could do, not pi over 15 radians. Okay. But yeah, so this fourth Maclaurin polynomial, right, is going to look like that. So you got the sum from n equals 0 to 4, right? We're going to stop at 4, the fourth power. The coefficients all look like this. Again, this the value of the nth derivative of our function at the center. Well, for our Maclaurin, the center is 0, right, divided by n factorial, and then times x minus the center, x minus 0, so just x to the nth. So if I write all this out, right, this would be f of 0 plus f prime at 0 times x plus the second derivative at 0 divided by 2 factorial, or just divided by 2, times x squared plus the value of the third derivative at 0 divided by 3 factorial, or divided by 6 times x cubed. And then finally, right, the value of the fourth derivative, I'll just put a little 4 in parentheses here, at 0 divided by 4 factorial, or 24, times x to the fourth. This is the fourth Maclaurin polynomial, fourth degree. So I need all these values, the f of 0, f prime of 0, right, all the derivatives at 0. Well, we know f is cosine of x. And then I'll just do the 4 derivatives, right? F prime would be negative sine x. And f double prime, or the second derivative, be negative cosine x. The third derivative be just sine x. And the fourth derivative, and you may remember this from like Calc 1, sine of x, cosine of x repeated every 4 derivatives, because when I get to the fourth derivative here, I'm back to cosine x. And then for this Maclaurin polynomial, for all these coefficients here, I'm plugging in 0 and then substituting. So the value of f at 0, right, the cosine of 0 is 1. So this is going to be 1 here, the lead coefficient, or the constant term, not the lead. Now f prime at 0 is, the negative sine of 0. Now sine of 0 was 0. So this first powered term is going to disappear. You'd have 0x. Then the second derivative at 0 would be negative 1, right? Cosine of 0 was 1 times negative 1. And the third derivative at 0 is the sine of 0, which is 0. So the third powered term is going to be 0, nothing, no third powered term. And then finally, the value of the fourth derivative at 0 is 1. Back to cosine of 0 again. Right, so I'm going to substitute those in, and we get our fourth Maclaurin polynomial here. So P4, right, fourth Maclaurin polynomial, that will use to approximate our cosine value is, f of 0, so 1 plus, f prime at 0 was 0, so this is gone, plus the second derivative at 0 is negative 1, so this would be negative 1 over 2 factorial, so minus a half x squared. And then plus, the third derivative at 0 was 0, so the third term is gone, the x to the third power term is gone. And then finally, the fourth derivative at 0 is back at 1 again, 1 over 4 factorial. So plus 1 over 24, 1/24th x to the fourth. And this should be approximately the value of cosine of x. All right, again, approximately, not exactly. And the closer to 0 we are, the better. Now, pi over 15, it's a little bigger than 1/5, 0.2 something. So it might be reasonably close. And we'll talk about error in another video after this. But for right now, we're using this to approximate the cosine of pi over 15. So this should be approximately this, this fourth Maclaurin polynomial at pi over 15. Okay, so this would be 1 minus, half of pi over 15 squared, and then plus, 1/24th times pi over 15 to the fourth, which I'm going to go to a calculator for this. Now, I'm actually going to graph both of these, right, cosine x in our polynomial, and then I'll just plug in pi over 15 to the polynomial, and we'll get our nice approximation. Desmos. Right, so here was our function. Right, the function we were given was cosine x. Right, and so there's a nice wave, right? Make sure I'm in radian mode here. Great. And then the polynomial, which I'll call, p of x, was 1 minus, half of x squared, so x squared over 2. And even that, you see how near 0, that's a pretty good approximation to the cosine curve. But then, the further away from 0 you get, it's not so good. It's deviating from the cosine curve quite a bit. But near 0, it's not bad. And then I throw on the next term, right, to get our fourth degree polynomial, plus, we had x to the fourth divided by 24, or 1/24th x to the fourth, and look at that. Near 0, with 0 at the center here, this purple graph and green graph are pretty much the same thing, right? This is a very good approximation to the cosine curve near 0, near x equals 0. But once again, the further away you get from 0, you see how the purple graph definitely deviates from the green graph. Right? But we're more near 0 here. Now, if I plug in, I'll do p of, pi over 15. If I plug in pi over 15 to the polynomial, and let me plot that point actually. Let me put point pi over 15, comma, p of pi over 15 as a point. Maybe I gotta get the comma out of the denominator there. Comma, there, now I have the point. Let's label that, right? So there's, pi over 15. Let me put the value down here again. But I think they wanted us to round it to like 4 decimal places or something. So when I plug in pi over 15 to the polynomial, to p, the value coming back is, 0.97814, and there's the point on that purple graph. Right here, I'll zoom in. And it's pretty close to being on that green graph. Now let's see what the I'm actually curious. What is f of pi over 15, right? The cosine of pi over 15. And you see, this is actually this is the actual value. And you see how it's pretty darn close, like 0.978147, and then it misses in the 7th decimal place, but it's good to 6 decimal places. So this polynomial is actually quite accurate. But they want to 4. So 0.971, if I round to 4 decimal places, 0.9781. So the cosine of 15 is about 0.9781. Wonderful. They take you through the whole process there like I did. Okay. All right, so another one where we're asked for a fourth Taylor polynomial. So that means it's going to be centered at a value other than 0. All right. If it was at 0, they'd call it Maclaurin. And so they're saying use the fourth Taylor polynomial for e to the x, f of x equals e to the x, at x equals 5, right? So that's the center. X equals 5 is the center now. To estimate e to the fourth power and round to 4 decimal places. All right, so again, very similar problem, but this time instead of being, centered at 0, centered 5. So the function we're given is, e to the x, which has some nice easy derivatives. And they want the fourth Taylor polynomial. So p of 4 of x, and they want it to be, a Taylor polynomial. So centered at, 5. So the value of a is 5 here. So that means this. We're doing this sum. The sum from n equals 0 to 4, right? Fourth degree polynomial here, fourth Taylor polynomial. But now the coefficients are a little different. It's not Maclaurin. It's centered at 5. So these coefficients of my polynomial are going to be the value of the nth derivative at 5, right, at the center, divided by n factorial. Right, so that's what the coefficients look like. And then not just x to the nth, but it's centered at 5, so times x minus 5 to the nth. Now, first term will be just what's f of 5, plus second term, when n equals 1, will be the first derivative at 5, divided by 1 factorial, times x minus 5 to the first, plus, then what's the second derivative at 5, divided by 2 factorial, times x minus 5 to the second, plus, then what's the third derivative at 5, divided by 3 factorial, times x minus 5 to the third. And then finally, right, we're going to the fourth powered term. What's the value of the fourth derivative at 5 divided by 4 factorial, and then times this x minus 5 to the fourth power. Right? Okay. Now, the nice thing about this function is, every derivative is the same. Every derivative, so nth derivative of this function with respect to x is e to the x. All right, so, every single one of these derivatives at 5 is going to have the value, e to the 5th. So so f of 5, f prime of 5, double prime, triple prime, fourth derivative, right? All those at 5 will be e to the 5th. And so I'm gonna actually do this. I'm gonna factor this out, this e to the 5th, because every single one of these terms is gonna have an e to the 5th. So this P4, right, is gonna be e to the 5th. Again, factored out, because every single one of these is e to the 5th, right? E to the 5th, e to the 5th, e to the 5th, e to the 5th. So I pull that out, and then we just have, 1 plus, and then 1 times x minus 5 to the first, plus 1/2 times x minus 5 squared, plus 1/6 times x minus 5 to the third, and then finally, plus 1/24, 1 over 4 factorial times x minus 5 to the fourth power, all that in parentheses there, all of that, because I factored out e to the fifth. And again, this should be approximately the same as the function f, right, which is e to the x, right? This should be very close to the graph of e to the x, especially around 5, right, centered at 5. And let me show you. I'll show you the same thing in Desmos again. So the function we were given, it was e to the x. So there's your graph, and I'm going to go near, now, this isn't going to be that great, but I'm going to go near 5, right, the way up here. La, la, la. Yeah, so here's where the graph crosses 5, right? So near here, z to the fifth is actually a decent size, over 100 some. And let me put that polynomial in, and you're going to see, let me see if I can actually plot this point, see where it is. 5 e to the fifth, and label it, and let's find this point. There it is. Okay, so here's near 5, centered at 5, and then you got this green graph going pretty much straight up and down almost. Now here's the polynomial, p of x, right, p sub 4. I said it was e to the fifth, right, times and then the quantity, and then 1 plus, you had x minus 5, plus, and then x minus 5 squared divided by 2 factorial, then plus x minus 5 cubed divided by 3 factorial, or 6. And then finally in here, plus, x minus 5 to the fourth power divided by 4 factorial, which is 24. And close the parentheses. And you see the black graph is basically on top of that green one. I mean, I know there's more of the black graph here, but if you look around this point, around where x equals 5 on the e to the x function, it's basically, it's a very, very good approximation. It's basically the same graph almost. Now they're asking us to estimate e to the fourth, right? In the question, they're asking us to estimate e to the fourth power, right? So this should be approximately, right? We said e to the x is about this. So e to the fourth power should be about this function here when x equals 4. So I just replace x with 4. So e to the fourth should be about e to the fifth times, and then 1 plus, negative 1, because again, 4 minus 5 is negative 1. So all these x minus 5s here will become negative 1. So 1 plus negative 1 plus, and then, negative 1 squared over 2 plus negative 1 cubed over 6 plus, and then negative 1 to the fourth over 24. Right. So again, all I'm going to do is go to my function and plug in 4 to our polynomial. So look at what's p evaluated at 4. Right, so 55.6549, right, if I round to 4 decimal places. Now let's see what e to the fourth actually is. Right, it's 54 something. So it's not the best approximation. And that's because 4 is like it's a unit. It's not close to 5. Close to 5 would be around here where I have on my graph. If I go to where x equals 4, we're down here. Well, let's do this. Yeah, when x equals 4. Yeah, see, there's where x equals 4 right here on the actually it's up here, but whatever. Right, they're not exactly the same, and you can see that here, right? P to the fourth, p of 4, the polynomial at 4 is 55.65. E to the fourth is actually, 54.59. So close, but not quite. Not as close as our last approximation was. And again, that's because we're further away from 5, further away from the center this time. But yeah, so we want this approximation here, 55.6549. All right, so 55.6549. Let's double check. 6549, 6549, great. All right, that should be good. All right. And again, they take you through the procedure here, finding these Maclaurin or Taylor polynomials. Okay. All right, so now in this question, it's just a true or false. Again, don't guess. I know you got a 50-50 shot on these, but remember, if you get things wrong, it starts making the assignment longer. It throws more problems at you. So we're asked to determine if the following statement is true or false. The Taylor series with the following expansion is a Taylor series for the function f of x equals e to the x at x equals 22. Now, this is e to the x again, so the derivative everywhere, all the derivatives, first derivative, second derivative, third derivative, fourth derivative, would be e to the x. And the center is at 22, right? So the value of all those derivatives would be e to the 22. You see that here, e to the 22 plus e to the 22 over 1 factorial plus e to the 22 over 2 factorial plus e to the 22 over 3 factorial is 6. So this is working out so far. And then you see all these powers of x minus the center, x minus 22 to the first, x minus 22 to the second, x minus 22 to the third. So yes, this expression that they're writing here, this series expansion, this is the Taylor series representation for e to the x centered at 22. So true. And again, they probably take you through how it would be developed. Not too much. All right. Okay. All right, so this is very similar. But this time they want the fourth Maclaurin polynomial for f of x equals e to the x. So we're centered at 0 again to estimate the square root of e, right? E to the half power, e to the 0.5. Right, so f of x equals e to the x. And once again, every single derivative of this is just e to the x. And since we're talking about Maclaurin, it says Maclaurin polynomial, Maclaurin series, we're centered at 0. Right? We're centered at x equals 0. So I'm evaluating all these derivatives at 0, and we're just going to get e to the 0, or 1. Right? So the fourth Maclaurin polynomial that will approximate e to the x. So again, the sum from n equals 0 to infinity of the value of any derivative at 0, which we saw was 1 over n factorial, and then times x minus 0, to the nth. So this would be 1 plus x over 1 plus, and then 1/2 x squared plus 1/6 x cubed plus 1/24 x to the fourth, and that's it, right? This is it. That's the fourth degree polynomial. And this should be approximately equal to e to the x, near 0 especially. So they want us to estimate e to the 0.5. So I'm going through and replacing all the x's with 0.5, right? So e to the 0.5 should be approximately 1 plus, 0.5 plus 0.5 squared divided by 2 plus 0.5 cubed divided by 3 factorial divided by 6 plus, and then 0.5 to the fourth over 4 factorial. And we have to figure out what this is. So again, I'm going to go to the Desmos calculator and do that. All right, so look, e to the x. So I'll just keep e to the x up, all right, because that was our function we were given. Now near 0, all right, now we're near 0. So here's the point 0, 1, that's on our graph. And Here's the polynomial, right? P of x equals 1 plus x squared over 2 plus x to the third over 3 factorial over 6 plus x to the fourth over 24. And I'll make this a different color, but it looks like it's blending. Yeah, you see this red graph, the polynomial is red. You see how near 0 the graph is very close to the green, right? It's basically on top of it. But then the further away from 0 you get, the worse it's getting, right? The more it deviates from the e to the x function. All right, so now what's the value of the polynomial at 0.5? And we're getting 1.6484. 1.6484. Now let's just see what is e to the 0.5. And look, that's pretty good, right? Because 0.5 isn't as far off from the center as our last problem. With the last problem, we were 1 unit off the center. Here, we're only half a unit off. We're closer to the center than we were in the last problem. So this should be a better approximation. Look at this, 1.648648. These are, the polynomial is accurate to the 3 decimal places here. That's not bad. But they want the polynomial estimate to 4, so 1.6484. So e to the 0.5 is approximately 1.6484. Same kind of deal. Use the fourth Taylor polynomial. So Taylor centered at 4 pi, x equals 4 pi. For f of x equals the sine of x, to estimate the sine of 4 pi minus 1, or negative 1 plus 4 pi. And of course, round the estimate to 4 decimal places again. So this is very, very similar to the previous several problems. So the function we're given is the sine of x. This time we want the Taylor polynomial, the fourth Taylor polynomial, centered at x equals 4 pi. All right, so the fourth Taylor polynomial here would be, again, the sum from n equals 0 to 4. We'll stop at 4. The value of the nth derivative of this function at 4 pi, right? The center is at 4 pi. Divided by n factorial, and then times, not just x, but x minus the center, right? X minus 4 pi to the nth power. So I need the values of these derivatives at 4 pi. There's f, f prime. We're going up to the fourth derivative. So f prime would be cosine x. The second derivative is negative sine x. The third derivative, negative cosine x. And the fourth derivative is, back to sine x again. Now, when I plug in 4 pi, 4 pi is coterminal with 0 if you talk about, coterminal angles. 0 and 2 pi and 4 pi and 6 pi, all those will have the same sines and cosines. The f of 4 pi would just be the same as the sine of 4. It was the sine of 4 pi, which is the same as the sine of 0, that's 0. All right, so the constant term in this polynomial is going to be 0. And then f prime at 4 pi would be the cosine of 4 pi, same as the cosine of 0, that's 1. So the first powered term is going to have a coefficient of 1 over 1 factorial, just 1. Second derivative at 4 pi is 0 again, sine of 4 pi. Third derivative at 4 pi is negative 1, right? Cosine of 4 pi is 1. And then the fourth derivative at 4 pi would be 0. So you see that the fourth degree polynomial is exactly the same as the third degree polynomial, right? Because you see the coefficient on the fourth power term is going to be 0. So if I write this stuff out, right, this P4, it'll be 0 for the f of 4 pi. And then the first term I'm seeing to be the first derivative at 4 pi, 1 over 1 factorial times x minus 4 pi to the first, plus, and then 0 times x minus 4 pi squared, then minus 1 over 3 factorial, so minus 1/6 times x minus 4 pi to the third, and then plus 0 times x minus 4 pi to the fourth. So that's it. Like I said, the fourth degree polynomial here is the same as the third degree because the coefficient of the fourth power is 0. And this should be approximately equal to the sine of x when we're near 4 pi or around 4 pi. Right? And they're asking us to approximate the sine of, -1 plus 4 pi. Plug in -1 or 4 pi minus 1. Right. So according to this, if I use my fourth Taylor polynomial here, I'm just plugging in -1 plus 4 pi for x in this polynomial. Now that would make each of these -1. Because, plus 4 pi minus 4 pi would go away. So we have -1 for the first term, then minus 1/6, times -1 cubed. And this would be -1, plus 1/6. So that's -5/6, which is -0.83333333, but threes repeat forever. I just know my sixths, you can go to calculator if you want. Now that is 1 unit off of the center, right? The center's at 4 pi. This is 1 unit less than that, so this might not be that accurate, but it's still an approximation, right? We're still using our polynomial to approximate this value. So I'm going to put that in to 4 decimal places. That'd be -0.8333, rounded to 4 decimal places. So -0.8333. Wonderful. All right, so that's done where I'm using the Taylor or Maclaurin polynomial to estimate the value of a function somewhere. So now I'm just going to finish up the find a Taylor or Maclaurin polynomial for a function, and then we'll be done, right? Because like I said, I don't want this is some heavy stuff, especially this remainder part. So I don't want this video to run more than a couple hours, right? We'll just stick to this first couple of objectives. All right. So now just, you've seen me doing this now for several functions, finding some sort of whatever degree Taylor or Maclaurin polynomial. So here's find the Taylor polynomial P3, so the third degree or third Taylor polynomial for this function, f of x equals 8 times x to the 1/3 power, or 8 times, the cube root of x. Centered at x equals 6, though, right? So 6 will be the center. I'm going to evaluate all the derivatives and stuff at 6 when I write the coefficients of this Taylor polynomial. So the function we're given, right, f of x is, 8 times x to the 1/3 power, or 8 times the cube root of x. And we're asked to do a Taylor polynomial to approximate this, but centered at, x equals 6. All right, so the third Taylor polynomial, right, P3, again, this is sum, n equals 0 to 3. Right, we can stop at 3. of the value of the nth derivative of this function at the center, right, at 6. Divided by n factorial, and then times powers of x minus 6. All right. So I need to go down to at least the third, to the third derivative here if I'm going to get to the third powered term. So first derivative of this function would be 8/3 times x to the negative 2/3, right, using the power rule for derivatives. Then the second derivative would be negative 16/9 times x to the negative 5/3. And then the third derivative would be positive 80/27 times x to the negative 8/3. And then I plug in 6 to all these. So this is going to be pretty ugly, as the cube root of 6 is not a nice number. So f of 6, right, plugging in the center is just, I'm just going to write it this way, 8 times 6 to the 1/3. I'll just write that. And then the first derivative at 6, again, I'm just going to write it this way, 8/3 times 6 to the negative 2/3, right, whatever that number is. The second derivative at 6, again, I'm just going to write it this way, even though it's ugly. Negative 16/9 times 6 to the negative 5/3. And then the third derivative at 6, the 80/27 times 6 to the negative 8/3, right? So again, I'm just gonna write those. So when I write out this polynomial here, right, when n is 0, we're just getting this 8 times 6 to the 1/3 and plus, and the first derivative at 6 divided by 1 factorial, so 8/3 times 6 to the negative 2/3, then times your first power of x minus 6, right, times x minus 6 to the first. Then plus the second derivative divided by 2 factorial. Now negative 16/9, when I divide that by 2, that'd be negative 8/9, so this would be minus 8/9 times 6 to the negative 5/3. That's the second derivative at 6 divided by 2, right? Times the second power of x minus 6. And then finally, third powered term would be the third derivative at 6, so this 80/27 times 6 to the negative 8/3, divided by, 3 factorial. That's divided by 6. So that would reduce, when you divide powers of 6, that would 6 to the negative 8/3 divided by 6 to the first, that'll reduce the power by 1. So that'd be 6 to the negative 11/3, all right? So 80/27 times and then 6 to the negative 11/3. That's the third derivative at 6 divided by 6 divided by 3 factorial times x minus 6 to the third power. There's what I'm going to type in here. Okay, and this polynomial should be approximately equal to, 8 times x to the 1/3 power, right, to our function. When we're near 6, right? The closer to 6 you are for x, the better the approximation will be. But yeah, so that's ugly as heck, but I am going to type it in. So 8 times 6 to the 1/3 power plus 8/3 times 6 to the negative 2/3 power times the quantity x minus 6. then minus 8/9 times 6 to the negative 5/3 power times the quantity x minus 6 squared. And then finally, plus 80/27. I think I accidentally wrote 80/26 on the paper. It's 80/27. 80/27 times 6, to the negative. I had negative 8/3, but then divided by 6 makes it negative 11/3. Right? Divided by 3 factorial. So to the negative 11/3 power times the quantity x minus 6 to the third. Let's see if it takes this. It's taking a bit here. Yay. All right, let's see how they have it written. They have this down here, which is equivalent to mine, just different looking. Okay. All right, so eventually this will come up, right? There we go. All right, good. All right, so this is going back to pretty similar to the first problem we saw in this video about an hour ago. They want a Maclaurin polynomial. So remember, this is centered at 0. And they want the third degree, the third Maclaurin polynomial, right? P3, for this function, f of x equals 1 over 7x plus 3. So f of x given here is, 1 over 7x plus 3, which, because I'm going to be doing derivatives, I'm going to think of this as 7x plus 3 to the negative 1. That'll make derivatives a little easier to do. And they want a Maclaurin. Again, Maclaurin means centered at 0. It's a Taylor series centered at 0. All right, and they want the third one. All right, so the third Maclaurin polynomial would be this sum, right, from n equals 0 to 3. And then the value of your derivatives at 0, right, the nth derivative at 0, divided by n factorial times x minus 0 to the nth, right, powers of x. Okay, so taking derivatives here, right, f prime would be negative, 7x plus 3 to the negative 2, and then times 7. So negative 7, times this. And then the second derivative, where I'm going out to the third derivative. Second derivative would be positive 14 times 7x plus 3 to the negative third. But then times, chain rule, I got to multiply by the derivative of 7x plus 3 there, so times 7. So that would be 108, 98, right? 70 and 28. So 98 times 7x plus 3 to the negative third. And then for the third derivative, be negative, now 3 times 98, that's 270 and 24, so 294, negative 294 times 7x plus 3, to the negative fourth power, but then times 7 again. Okay, so, that's basically, 7 times 300 is 2100, and then take away 6 times 2100 minus 42, so 2058, negative 2058. Right, and then times 7x plus 3 to the negative fourth power. And then for these coefficients of my polynomial here, right, I'm plugging in 0 for x, plugging in the center, right, the f of 0. That's 1/3, right? That's 3 to the negative 1, so 1/3. F prime at 0. Now 3 to the negative 2 is, 1/9, but you got negative 7 in front, so this is negative 7/9. F double prime at 0, where you got 3 to the negative 3 is 1/27th. And then 98 in the numerator, so 98/27ths. And then the last one, right, the third derivative at 0. 3 to the fourth is 81, so 3 to the negative fourth is 1/81. Thing is, though, 3 goes into 2058 evenly. All right, 3 goes into 2058 686 times. So this is negative 686, and then over 27, right? So one of the 3's goes into that evenly. Yeah. Just double checking. 3 times 6 is 18, then 25, 3 times 8 is 24, then 18, 3 times 6. Yeah, so 686. All right, and then I'm popping these in and dividing them all by n factorial, right? So that might change some things too. So this third polynomial, third Maclaurin polynomial, to approximate the value of this function near 0, is 1/3, right, that's f of 0. Then plus, f prime at 0 divided by 1 factorial, so just minus 7/9 times x. Then plus, now this divided by 2 would be 40, 98 divided by 2 is 49, so that's 49/27ths x squared. And then minus now 686 over 27. We're dividing that by 3 factorial. Now 2 goes into this 343 times, and that's not divisible by 3. So when I divide by 6, that's dividing by 2 and by 3. If I do 2, that'd be 343, and then there'd be another 3 down here making this 81. So 343 over 81 x to the third. And sorry about the clutter there, but so that's the third degree polynomial that will approximate the value of 1 over 7x plus 3 when we're near x equals 0. And I'll type all that in. So the constant, 1/3, then minus 7/9 times x plus 49/27 x squared minus 343 over 81 x to the third. And there should be, if I did things correctly, the third degree polynomial that approximates that function. Wonderful. All right, and that looks like it for that. So again, all I'm doing in this video is just this first bold heading. So maybe tomorrow and Sunday or over the weekend, I'll do the rest of them. There's already a hour 20, hour 15 in here. So I don't, again, this Taylor theorem with remainder, I know it's only one objective, but it's long. All right, I gotta. It's an involved one. All right, so that's it for me for this video on Taylor and Maclaurin series. This bold heading. Look out for future videos on the rest of the objectives from this 6364 assignment. As I said at the top of the video, please understand that the questions I saw here may not be exactly the same questions that you see when you work on the assignment yourself, but the problems are hopefully similar enough in the way I did them, the setup for them, are similar enough that you can get help from them when you work on the assignment yourself. And thank you very much for watching.